continuing my lecture series, Introductory Physics. Doesn't say that right here. I should put physics right there so we all know physics, right? Okay. And I'm going off the structure of Halliday, Resnik, and Walker, edition 9. But pretty much any calc-based course is going to do the same kind of stuff. Maybe not exactly the same order, but close enough. And so now we're in chapter 3, and chapter 3 is about vectors. So chapter 1 is about units. Chapter 2 is motion in one dimension. If we want to do motion in 2 dimensions, we need vectors. So let's just be clear here. Scalars, vectors. So a scalar is a quantity that only has one piece of information. So I'm going to give some examples here. Time, mass. I was going to say color, but actually you could write color as a vector. Temperature. Energy. That's a common one that we're going to use later is a scalar. I'm trying to think of another good scalar. Density. That's kind of dumb. That was not a good idea. Okay, now let me give some ideas of vectors. Position. Displacement. And I'm going to tell you why. Velocity. Force. These are just some examples to start off with. So all of these you have to represent with more than one piece of information. So this is one, more than one. So, a lot of times in, I remember in Despicable Me, the villain was vector. I have both magnitude and direction. That's 2 pieces of information. That's okay, and it's not necessarily wrong, but I think it's better to think of it as more than one thing. Okay, more than one thing. So position, you could think of this in terms of x, y, and z axis up here. It would have an x, y, z coordinate. So we'd represent that as an arrow. So that's one. Displacement too, if it goes from here to there, you have to know which, not just how far away it is, but which direction. And if it's in 3 dimensions, that's 3 values. So that's 3. Velocity. In 2 dimensions, you can represent this as a magnitude and direction. In 3 dimensions, you can represent this as a magnitude and 2 directions or 3 components. So x, y, and z velocity. And same with force, x, y, and z force. And so I like to emphasize straight off the bat the 3-dimensional nature of vectors. Okay, so all those things are vectors. Number one thing about vectors, if I want to write the vector velocity, I would normally write that like that, v. And there's really the best way to represent a vector like v is with its 3 in Cartesian coordinates. I don't think you do non-Cartesian coordinate vectors in introductory physics. It does come about later. Would be represent this as its 3 components. So you could write this as Vx. I'm looking at this book. It uses I hat plus Vy j hat plus Vz k hat. So that's how much in the x, how much in the y, how much in the z. And I hat, j hat, and k hat are the x hat, the x direction, the y direction, the z direction. Another way to do it would be like this. Vx x hat, I like this better, plus Vy y hat, I like that better, plus Vz z hat. And I'm going to talk about these unit vectors in just a little bit. Finally, there is this notation, Vx, Vy, Vz, as this ordered pair with angle brackets. And that's just a little bit shorter form notation, so it's a little bit easier to deal with. So let's talk about this notation. I'm going to use 2 dimensions because it's easier to draw 2 dimensions on paper than in 3 dimensions. So one of the ways that we represent a vector in 2 dimensions, I'm going to use the xy plane, is with an arrow. So let's talk about a position vector. And I'm going to call it, I use this vector, I'm going to call it r. So just in general, if we put an arrow over the variable, that's going to be what we denote as a vector. So there's 2 parts in 2 dimensions. There's an angle, and it doesn't have to be with respect to the x-axis. It can be. It doesn't have to be. And then the magnitude, which would be the length. So we can write the magnitude. Let's just give it That's fine. I'll give you some numbers in a little bit. So one of the ways to deal with this is to say, okay, look, if I want to go from here to there, I could go a distance r at some angle theta, or I could go this way, and I'll call that a distance rx, and then I could go this way, and I'll call that a distance ry. And you'll see that I have, since x and y are perpendicular to each other, I have a right triangle. And so from that, I get the following relationships. I can say the sine of theta is going to be opposite over hypotenuse, so it's going to be ry over the magnitude of r, like that. I could write it as just ry over r. So this is a little bit burdensome, so some people don't like to do that. So that would just be the magnitude, the length of it, how far. It's a scalar value, okay? But that has to be true. And so from that, you get ry is r sine theta. In this case, right, because of the way my angle is. Don't treat this as always true. It depends on where that angle is measured from. And then I could do the same thing. Cosine theta is going to be adjacent over hypotenuse. So that's rx over the magnitude of r, or just rx over r if you want. And then we can say rx is r cosine theta by just multiplying both sides by r. So if I know the magnitude and the angle, I can find the components rx and ry. The same is true or the opposite is true if I know the components, I want to find the magnitude. If I know rx and ry, I can say r is the square root of rx squared plus ry squared. Right, because it's just a Pythagorean theorem. And then I could say theta is going to be the inverse tangent of ry over rx. It's tangent's opposite over hypotenuse, so if I take the inverse tangent both sides, I can find the angle. And that'd give me the angle with respect to the positive x-axis. So you got to be careful about these things. It always helps to draw a picture. Just be very careful about what you do. But you'll see here we have our first thing that's really important, adding vectors. So let's just start a new page. And yeah, I'm going through this stuff like blindingly fast. Okay, you're going to have to practice with this stuff. And I'm going to show you one way to calculate things in a little bit. But there's a lot in this chapter, and they kind of just throw it all together at the same time, and then use it later. But you're going to use vectors. If you're a physics major, you're going to use it. If you're not a physics major, but you're taking this course, welcome. Hope you have a great time. But the first semester uses vectors. The second semester, electric fields and magnetic fields is what the whole focus is on. It has a lot of vectors. Okay, so let's add vectors. Let's just take some random vectors. I'm going to call it A and B. So let's say I have a vector A and a vector B. And I'm representing these as arrows. So in this graphical representation, the length is the magnitude is represented by the length, and the direction is represented by the direction. So I have two different vectors. Now, with that being the case, it doesn't matter where I move this vector as long as I keep the same direction and length. It's the same vector. So if I want to say the vector C is the vector A plus the vector B, right here you'll notice one important thing. We can add vectors, but you cannot add a vector and a scalar. If you add two vectors together, it has to be equal to a vector, right? Or you can't use the equal sign right there. So that's important. So if I want to add these two vectors, the easiest way is to say, I'm going to take the vector A, I'm going to redraw it right here, hopefully very close to the same thing. I'm going to take vector B, and I'm going to put it right here. So I'm going to put the beginning of B at the end of A. And if I do that, the A plus B will be from the beginning of A to the end of B, and it will be this vector right here, C. Okay, I'm going to need to find my pen. I need to use a colored pen. Here's one. How sharp is that? Sharp. I had a good red pen. Oh, here's purple blue. Let's see. Do I have a... Okay. Oh, that's a... Is this one right? That's good enough. Okay. So here's a trick. Because suppose I say the vector A is represented as some x component magnitude times a direction x hat plus a y component in the y direction, and I do the same thing for b. B is bx x hat plus by y hat. So if I draw that, let's draw the x components. So here's my x component of a. This is actually ax times ax times x hat. And then my b component is right there, right? And then I will draw my y components like that. And so now you'll see that I have two right triangles. It turns out that vector addition does not depend on order. So that means that I can change up these orders. I'm going to draw it like this. I'm going to start here with ax, and then I'm going to call that ax. And then I'm going to do bx, and then I'm going to do ay, and then I'm going to do by. And so now what I've done is take two vectors, break it into 4 vectors, and then add those 4 vectors. But we have something really nice here, because if I have 2 vectors in the same direction, those are easy to add. If I have 2 vectors in the opposite direction, those are easy to add. If I have 2 vectors that are perpendicular, those are easy to add, right? I can deal with all those situations. If I have some weird situation like this, and it's not a right triangle, you can use the law of sines and cosines, that's true, but don't do that. Just trust me on this one. So what I'm going to do is add the x's together, and then I'm going to add the y's together, and then this is going to be my resultant. So if I redraw that, I have, I don't know why I'm using blue, ax plus bx, ay plus by. And then here's my resultant. So then if I wanted to, I could just write this in terms of the x and y components, or if I wanted to, I could find this angle and this magnitude right there. So the answer is, up here, if I add those 2 vectors, I don't have to do it graphically. I can do it algebraically. I just add these 2 together, so I get ax plus bx x hat plus ay plus by y hat, and that's the answer. And it doesn't matter if these are positive or negative components. It's all good. Okay. Components of, I'm looking at my list here. Unit vector notation. Do they do unit vectors? I'm not going to go over unit vectors. It's really important in the second semester, but this book doesn't cover it, so it just talks about the unit vector notation, x hat, y hat, z hat. X hat is a vector in the x direction, and in fact, if you wrote that as a vector, it'd look like this: 1, 0, 0. Y hat is 0, 1, 0, and z hat is 0, 0, 1. They're actually super useful in that they have a magnitude of 1, so when you multiply it, it doesn't change the magnitude of the vector, and it has a no units, so it also doesn't change the direction. So they're very useful in terms of these things. And I think that the book just says kind of let's just plow forward, so let's do that. But that's how you add vectors. You can add as many vectors as you want. You just keep on adding up the components. You can subtract vectors too. Because if I have a vector, I'm going to give an example here. C equals 2x hat. No, I'm going to use A and B. A vector is 2x hat plus 3y hat. And I'm just going to use 2 dimensions. B is the vector 1x hat minus 2y hat. Now let's say I want to do A minus B. A minus B. Well, there's 2 things you could do. Number 1, I could say, well, what's the negative of a vector? Negative b is just going to be negative 1 multiplied by each component. So I get negative 1 x hat plus 2 y hat. So then I could say a plus negative b. So I could say this is equal to a plus negative b. Or I could subtract and just subtract the vectors. So either way, I get 2 minus 1 is going to be 1 x hat. 3 minus negative 2 is going to be 5 y hat. I don't know why my paper's blowing up like that. So that's how you subtract vectors. In fact, you can multiply any vector by a scalar, and you just multiply each component by that. So if I have that same vector a, let's say 2a, all I have to do is multiply 2 by 2, so it's going to be 4x hat plus 12 y hat. And whatever units the product has is the unit that this has. Okay, now they have, so you could divide by a scalar, you can multiply by a scalar, it doesn't matter. You cannot multiply two vectors together, you cannot divide two vectors by each other. But you can do a vector operation. This paper is messed up. The vector operation, there's two. They're called the scalar product. So if I have the two vectors, I'm going to write them as I'm going to use this notation, 1, 2, 3, and B is -2, 1, 1. And they have some units, but I don't really care. So how do I operate these two vectors together? There's a way I can operate them together to get a scalar value. So I can say W equals A dot B. It's also called the dot product, scalar product. And what you do in this operation is you take the x components and multiply them together, the y components, multiply them together, the z components, multiply them together, then add all up. So this would be ax bx plus ay times by plus az times bz. And you'll notice that this is a scalar, 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 so I can add them together. In this case, I'd get -2, 1 times -2, plus 2, 2 times 1, plus 3, 3 times 1, which would be 3. And it would have units, whatever that would be. There's another way to find the vector product. I could also say W is the magnitude of A times the magnitude of B times the cosine of theta, where theta is the angle between them. So sometimes you know that angle and you don't know the components, then you could use this form. But they are identical. Okay, then there is the vector product. Vector. What happened right there? Vector product. This is a way to take two vectors and operate them together so that you get a vector answer. And so we would write this as, I'll call this as F vector is A cross B. So we sometimes call it the cross product. Now, the answer is not so easy here, but I'll just write it out, and I'm not going to explain it because I don't think we're quite at that level. If I know the components of A and B, then this would be why did they write it? I'm looking at the way they wrote it. Oh. They didn't write it out. Okay, I'm not going to write it out because you're not going to use it in this semester. But I will say this, the magnitude of this vector is the magnitude of A times the magnitude of B times the sine of the angle between them. Okay, and then we'll deal with this book doesn't deal with the exact cross product, so I'm not going to do that either. What I am going to do is to show you the best ever vector calculator that will be super useful in your course. So let's jump over here to the computer and I'll explain it. So this is awesome. This is Web v Python. I'm using this in Trinket.io. I will give you two online links. They both work on in a web browser. You don't have to install anything. And I think it even works on your phone. I'm pretty sure it does. So if you're allowed to use your phone as your calculator, maybe this will work for tests and stuff. That depends on your instructor. I let my students do it. Okay. So this is a form, essentially a form of Python. And it does a whole bunch of great stuff. But you don't need to change this first line here. It's automatically set. But other than that, we can make variables. I'm going to do a super quick calculator example. I'm going to make variables, scalar variables, and then I'm going to make vector variables, and then show you the operation. So let's just say A equals 1.5. I can print that which is stupid, I know, print A, and now I'm going to run it, and you may think that's just dumb, because obviously that's what it is, and you get 1.5. Is that big enough? I feel like it's not big enough. There, maybe that's big enough. I can make another variable. Let's call it b equals negative 0.234. I'm just making up stuff. Now I'm going to print a plus b. And so it does indeed add them. So you can do a whole bunch of operations here. I could do a plus b squared, and star 2 is squared. Get it right there. I can do the square root of a. Square root is built in, like that. And so there's a whole bunch of operations. I don't want to get into this too much. It's just super useful in a lot of ways. If you want to make it print out really nice, you could actually say this. I could do c. Let's see. C equals that, and then print c equals c, and then I'm going to put units. If you want to make it, but you can save this, and then you can rerun that later, and so it's super useful. What about vectors? Let's make a vector. A equals vector 1, 2, 3. Print A. And you'll see it does treat it as a vector. Let's make another vector. B equals vector negative 1.3, 0.5, 2.1. Making up stuff on the top of my head. Now, let's say the vector C, case does matter in Python, so capital C is different. C is going to be A plus B, print C. I could write equals C and all that stuff. But there's my vector addition problem right there. Isn't that awesome? I can also find the magnitude of a vector. So I can say, let's give it a name. C mag equals mag C. So mag is a built-in function in GlowScript VPython that returns the magnitude of a vector. And so if I print that, it goes right there. Super useful. I can multiply vectors. I can say, let's say print A times C. So here A is a scalar, so I can do a scalar operation and multiply them and add them and print that out, and it does. If I did this, if I did A times C, it's going to say, wait a second. You can't multiply a vector and a vector. You can do the dot product. Okay, so I can do the dot product, and I'll do it right in here, dot A, C. So dot is the dot product between vector A and C. It's a built-in function in Python, and I can print that out, and it should give me a scalar value, and it does. I can do the cross product. It's cross. And you'll notice that gives me a vector product. Okay, one of the fun things is this. Suppose I have vector A and B, and I want to find the angle between them. I'm going to put a comment in here. I'm going to say A dot B equals A, B cosine theta. Remember that? So that means that cosine theta is A dot B divided by the magnitude of A times the magnitude of B. So let's do this. Theta equals dot A, B divided by mag A times mag B. And then I'm going to say print theta equals theta times 180 over pi, because it does it in radians and I want it in degrees, and that's that. And there you go, 36 degrees in between them. Okay, one more thing, and then I'm going to stop. Let's do one more vector. Let's say r equals 2.3, theta equals 40 degrees times pi divided by 180. So I have it in radians. Let's do this I'm going to call this r mag. So I want the vector r, so I can say r equals vector r mag times cosine theta, r mag times sine theta, 0. And then I'm going to print that. Let's just print it like that, print r. So I can create this vector from a magnitude and a direction if I want to. And there's my vector. Okay, So there's a whole bunch of stuff that we're going to do with vectors. I wanted to show you this Python because I think it's super awesome and super useful. I'll put the links, like I said, down below to trinket.io. If you do a trinket.io and you go to a new trinket, let me make this a little bit smaller so I can see it. I'm going to click up here, new trinket. Right there, you'll see Python, Python 3. You want to do GlowScript. Make sure you do GlowScript. If you do Python up here, it will not have the vector class input in it. If you do Python 3, it will not have it. And you can't save it without having a paid account. But the GlowScript you can use for free. This is the other site. It's GlowScript right here. You do need to sign in. You can sign in with your Google account to create stuff. For the Trinket, I'm not sure that you do, but you should do it anyway. That way you can save your programs. But this is essentially the same thing. The other one just looks a little bit different. So, okay, chapter 3 is in the books. Hope that helps.